So in order to pick up where we left off from before, we needed to understand how we can know how to completely solve a system of differential equations in addition to the eigenvalues and eigenvectors we were discussing previously. So there are two facts I want you guys to remember, and both of these facts are going to seem very familiar to you. First fact, we'll call them facts. Number one, if, okay, x1 of t, okay, and x2 of t, and by the way, these are the column vectors, are two solutions they are two solutions to a homogeneous system. Okay. Then C1 times our first vector, x1 of t, okay, plus C2 times our second vector of t, and let me go ahead and make that look a little nicer, is also a solution to the system. And you'll see that's going to become very useful for us later on. Second fact, suppose, and this is where things are going to seem very familiar to you, suppose that A, okay, is an n by n square matrix, or n by n matrix, okay, and suppose okay, that x1 of t, all right, x2 of t, okay, and so these are solutions, and then xn of t, all solutions, right? So I'll just make sure that's explicit, are solutions to a homogeneous system. Okay, now that's true. Let's go ahead and define the following. We have some other matrix, which I'll call X, which holds the vector of unknowns here. Okay. In other words, okay. In other words, X is a matrix okay, whose ith column, so ith being, anything between 1 and n, but it could be 1 or it could be n, whose ith column is the ith solution. Okay, so the second column is the second solution. The nth column is the nth solution, and so on. That's all this means. Okay, now define the following. W equals determinant of big X. Can you guess what this is? This is the Wronskian, and it comes back again to help us save the day, even at the very end of the semester, which is why I made the Wronskian such an important fact for you guys all throughout the term. The Wronskian again plays a crucial role in helping us understand solutions for first order differential equations. So we call W the Wronskian, as you guys know, which is spelled Wronskian. Okay. And you guys already know some things about this. Number one, you guys probably know if W does not equal 0, right, then the solutions and here's the big piece right here, then the solutions form a fundamental set, or FNUND, fundamental set of solutions, okay, and the general solution okay, then the general solution to the system is X, and this will be our vector, which has our general solution. This will equal C1 X 1 of t, okay, plus C2 X 2 of t plus Cn Xn of t. There we have it. That's the key important second feature. So even if we use those eigenvalues and we find those eigenvectors and we solve our general system, we still need to check if the solution is completely general and forms a fundamental set of solutions. And the way we do that is by computing the Wronskian. So therefore, the Wronskian is a very good bookmark between a midway point and a final conclusion. We use the Wronskian to determine linear independence, right? Because if we had, or if we do have a fundamental set of solutions, then the solutions are also going to be linearly independent. Nice connection with linear algebra. And also, if we have a set of linearly independent solutions, then they will also be a fundamental set of solutions, since the Wronskian will not be 0. So that's a key observation I want you guys to remember, and that's going to prove to be very helpful for us as we start to solve systems of linear differential equations, which we'll do in our last video, and then next week I'll show you guys how to solve one more, and then how to apply Laplace transforms to these systems of linear diff EQs. See you soon.